Hello dear cadets, we already have started the module number 2, slope and deflection of the beam. First two cases we already have covered of simply supported beams. One is of point load, second is of uniformly distributed load. Now we are going to start the case number 3 of uniformly varying load. So let us go to the case number 3. Okay. Now we'll start the case number 3, that is simply supported beam carrying a load whose intensity varies uniformly from 0 at one end to W per unit run at the other end. Okay, so for this we have to find the maximum slope and deflection. So half of the derivation I already have written here. These are the various loads I have shown. Before that, these are the total loading that is acting on this. How this loads has come, that I will first show you, and then this diagram will refer later to solve the derivation. Okay, so let us consider a simply supported beam. So this is our simply supported beam AB. Okay, it is of the length L, so let it be of the length L. We know there are the end reactions at the B, that is VB, at the A it will be VA. And what does it carry? It carry a load whose intensity is 0 at one end. So let 0 is the loading at the end B, and intensity varies to W at the other end. So at the end A it is W per unit run. Okay, and it varies uniformly, so the straight line will come there because it is uniformly varying. So right angle triangle will be formed. Okay, so we know what is the total load due to right angle triangle. It is nothing but the area of the triangle. So that will be W into L by 2, base into height by 2. So this is the total load I am showing here. WL by 2 will be the total load. Okay, and where does it act? It is always at the center of the triangle, that is at L by 3 from the end A. Is it? This load I have shown to calculate the reaction values. So let us calculate first reaction values. Okay, so it will be calculated like this. VA plus VB will be the total load. What is the total load? WL by 2. Okay, and to calculate the reactions I will take moment at one of the end. So let us take moment at end A. Okay, so it will be summation MA equal to 0. So then it will become VB into L minus WL by 2 into L by 3. So if you calculate VB, L will be cancelled. It becomes WL by 6. Put this VB here in this equation. Then VA will be coming WL by 3. Okay, you can calculate it mathematically. You will have these reaction values. Once we get these values, we'll put these values at the VB and VA. So same is shown here in this figure. After calculating the values of VA and VB, they are put here. Okay, after that, what is our next step? Next step, we always take a section. So in this span AB, I will be taking section X. So let this section X is being taken at the distance X from the end B. Okay, section X is taken. It means that we have to find the load which is acting on this span BX. BX, that is a small triangle. So to calculate that load, we have to consider some load intensity here at the height, that is at the section. So what we considered is WX. Okay, so same thing is shown there. WX is the load intensity at the section X at the distance X from the end B. So we have to calculate this value of WX. How can we calculate it? By similar triangle principle. So if I apply similar triangle principle to this smaller and this larger triangle, it will be WX upon X is equal to W by L. Is it? So WX then become W into X by L. This is WX. What is the total load on the smaller triangle? Total load on span BX, you can say. BX is nothing but area of this small triangle. area of the small triangle is 1/2 base is x into height is wx. Okay, if you replace this value of wx as w into x by l, so the total load will become wx square by 2l. So what this load is, this is the total load acting on the smaller triangle. And where is it going to be at? It is at centroid, which is at x by 3 from section. Got it? So this is the load which is going to be act here like this. Wx square by 2l is the magnitude of the load acting at the distance x by 3. Okay, so same figure after calculating all these loads are shown here. Okay, this is the total load. Vb, Va are the reactions. Wx square by 2l at the x by 3 is the load what we have found. This is the load which is required to find the bending moment. You see, same thing is repeated here. The reaction value is Vb and Va as this, and the total load is Wx square by 2l at x by 3. Now we'll go for finding the expression for slope and deflection. Every step or every derivation always start from this equation. We know EI d square y by dx square is equal to total bending moment at the section x. So what is total bending moment at the section x? Let us go back to this figure. Total bending moment will be on this part is, if you see, WL by 6 into x minus Wx square by 2l into x by 3. Only these two loads are acting, so two loads will have the two moments. Same is written here. Okay, so EI d square y by dx square is WL by 6 into x. If you calculate that, this will come this. This is your equation number 1. From this, what we have to calculate is slope. We know dy by dx is the slope. So integrate equation number 1 with respect to x. So if we integrate this become EI dy by dx. Integration of this is WL by 6 is constant. Integration of x is x square by 2. Is it? W by 6l is constant. Integration of x cube is x raised to 4 by 4 plus c1 is the constant of integration. This becomes your equation number 2. Now to get the deflection equation, again integrate 2 with respect to x. If you integrate it by simple integration formula, c1x plus another constant c2 will be added to this. This came by general integration rule. Okay, so this is our expression number 3, which is for deflection, which is applicable to every point between a and b from 0 to l. Now to calculate the values of the constants c2 and c1, we'll use the known condition. What is the first known condition? At the a and b, if you see here, at the a and b, x is 0, and at the a and a, x is L. Here x is 0, y is 0. Here x is L, y is 0. These two are our known condition. So first known condition is at a and b, put x equal to 0, y equal to 0 in the expression number 3. So if you put it here, y is 0, so LHS becomes 0, x 0, x 0, x 0, so only C2 will remain, so C2 naturally becomes 0. Now to find the value of another constant C1, we'll use another known condition, that is at the a and a, x is L and y is equal to 0. Put in the same expression number 3, you will get the another constant C1. Once we get the value of C1 and C2, now we can find the expression for slope and deflection in the form of the numbers. Okay, so let us put back this value of C1 in the expression number 2. Okay, so put C1 in the expression number 2 here. Do it mathematically. So it will be the expression number 4 that is going to be calculated or formed. Okay, so this is our general expression after putting the value of C1. C1 value is put here. C1 is this. This has been taken here. So this is our expression number 4. Got it? Now this is general expression of the slope we have got. Now we can find the slope at both ends. We know at the a and b x is equal to 0. So put in the expression number 4. If you put x equal to 0 here, you will simply get the slope at the a from this. Put x equal to 0, so this is cancelled, x 0, this is cancelled, only this is going to be remain at the b. And similarly at a, x is equal to, sorry, something has gone wrong, I think. At b, x is equal to 0, so at b it will come minus 7wl cube by 60. At b I am talking, yes. And at a, what is another condition we'll put? X is equal to L. If you put x is equal to L here in this equation, everything will be taken, and if you calculate it, the value will then come WL cube by 45 EI. So slope at both ends are now found, at B and at A. Okay, this is at A, this is at B. Okay, mathematically you will get these values. The slope part is now over. What remains is now the part of the deflection. So deflection part we'll see little later. You can see this, you can check the calculations. Okay, I will upload the next video. In that I will be continuing from this to give the expression part as well as the numerical. Got it? Okay, thank you.